Welcome to the styrene family, or the Styrenics when we're talking about resins. This is polystyrene and its copolymers. Styrene family consists of polystyrene and copolymers of styrene. These include ABS, acrylonitrile, butadiene, and styrene, or SAN, styrene and acrylonitrile. Also styrene butadiene rubber, which is a 25 to 75 ratio of styrene and butadiene, and then K-Resin, which is a 75-25 ratio of styrene to butadiene. So in this case, 75 styrene, 25% butadiene. Same comonomers, different ratios, very different properties. When we're looking at the global use of styrene monomer, this is polystyrene versus its copolymers, so about 42.5%, and then a mixture of the other comonomers of styrene. This is polystyrene. This is the repeat unit for polystyrene. Polystyrene is made from styrene. Seems pretty self-explanatory, but once again, as I have said before, and I will say until I die, the brackets and the N shown here show that this is a polymer, polystyrene. This was commercialized by Dow in 1937. It had a lot to do with developing the synthetic rubber industry during the years immediately before the United States got into World War II and during World War II. So in 1938, there were 0.2 million pounds sold. By 1940, this had gone up an order of magnitude. It had doubled by 1942, and by 1950, 200 million pounds of polystyrene was being used. So that was directly driven by the need for development of synthetic rubber during World War II. The first time polystyrene was on the scene, it was in 1839. Edward Simon isolated polystyrene from a natural resin, but he wasn't really sure what he had discovered. Until 1922, that was kind of how it stood. Hermann Staudinger published a theory, and his theory was that the long chains of polymeric styrene molecules is what was actually present in Simon's discovery. In 1953, Staudinger won the Nobel Prize in Chemistry for this research. So if getting a Nobel Prize is on your horizon, please understand that it may take over 30 years for the entire world to appreciate your genius. That's what I tell myself, anyway. In 1930, BASF developed a method for the commercialization of polystyrene. While it was developed in 1930 at BASF, the United States really didn't have access to that because BASF is a German company. Therefore, in 1938, we didn't have a really good relationship with Germany at the time, so Dow started to introduce polystyrene products onto the U.S. market. In the early 1940s, this was primarily driven by the Dow Chemical Company. Ray McIntyre from Gardner, Kansas, invented polystyrene foam, or styrofoam. This was entirely an accident, and what he was actually trying to do was come up with a flexible electrical insulator. Instead, he came up with the product that we know as the packing peanut. When we're talking about the energy requirements for making thermoplastics, polystyrene is the highest of the commodity thermoplastics. PET is listed here to give you an idea of how it compares, and PET is a quasi-commodity plastic. So it is the highest of all in terms of energy requirements. Polystyrene, unlike the predecessors we've talked about in the commodity resin market, has zero crystallinity. And that's one of the major advantages of it. K-Resin has glass-like clarity. The TG of polystyrene is 100 degrees Celsius. It is hard and brittle. Above 100 Celsius, it softens easily. It does not exhibit a sharp TM because it is amorphous, so it mainly has a softening point, and this is about at 107 degrees Celsius. When you talk about Vicat softening, the actual definition is the temperature at which a specimen is penetrated to the depth of 1 millimeter. They use a flat-ended needle with a 1 millimeter square circular or square cross-section, and you use a load of 10 newtons for a Vicat A and 50 newtons for Vicat B. The reason that polystyrene is used is because it has brilliance in appearance, a high refractive index. And how it compares to glass is polystyrene has a refractive index of 1.59, glass has a refractive index of 1.5 to 1.65. So light goes through it much like it does glass. And in other words, low optical dispersion. You don't get a lot of scatter. It's nice and clear. Its refractive index also doesn't vary widely by change of wavelength, and that makes it really good for applications like lenses or optical piping. This has good resistance to water absorption and does not require pre-drying prior to processing. Good electrical insulation properties. It is a very good low voltage insulator. It has good chemical resistance to acid, alkali, and salts, but it is easily attacked by ketone solvents. It is easy to bond polystyrene parts, and you can use aromatic and chlorinated hydrocarbons like methylene chloride to do that. Polystyrene has high surface hardness and gloss, but is easy to scratch it. And it has really excellent aesthetic values. It has no taste, odor, or toxicity compared to other things that are clear. When it comes to polystyrene, there are some issues. Unmodified polystyrene is amorphous in nature, and because it is amorphous, it is pretty brittle. It has poor impact resistance as a result. So there is something called HIPS, or high impact polystyrene, and that is a blend of 15% butadiene and polystyrene to give it better impact properties. Polystyrene is very susceptible to environmental stress cracking as well. One way to improve that is to anneal the parts after processing, and that enhances a little bit of the crystallinity in the polystyrene part and gives you some environmental stress cracking resistance. Polystyrene is very susceptible to UV light. It turns yellow on exposure to sunlight, and you can use some UV stabilizers to correct this. It also happens in its copolymers as well. So anything with a styrene monomer in the backbone, and ABS is the big one, turns yellow on exposure to sunlight. I had a washing machine that was in a room with a window, and everywhere the light would come in from the window on my washing machine that had ABS trim turned yellow. I also have some baby gates that are exposed to light, and the sides that are pointing toward the window have turned yellow because of the styrene in the backbone. So this is why polystyrene isn't appropriate for outdoor applications. You're not going to get stability of color. And color is very important, especially for specific brands. It has a low softening temperature of 107, and so this limits the use of polystyrene. It's good for processing, but if it softens at 100 degrees Celsius, it will do so in your part as well, so you're not going to have structural integrity of your part. It is not flame resistant, and it burns with a sooty smoke. And when you incorporate flame retardants into polystyrene, it's only partially susceptible, so it's not good for anything that may be in a situation where it may be exposed to flame. It is very susceptible to hydrocarbon solvents, and it quickly deteriorates on exposure. Sometimes you'll get a cheap watch that has a polystyrene top crystal, and you can tell if you try to clean that sucker off with acetone, so don't do that. It will cloud up, and you will not have a nice clear crystal anymore. Polystyrene also requires an anti-static agent. Very quickly builds up static, and oftentimes they use cotton and wool fibers as an anti-static agent in the formulation. It improves the conductivity and dissipates the charge due to the low water affinity of polystyrene. Generally, you're not going to use polystyrene for any outdoor applications because of the susceptibility to UV attack. ABS is one of the most widely used copolymers of styrene. ABS is a terpolymer, meaning it has 3 comonomers in the background. This was introduced in the 1950s. It is considered a quasi-commodity thermoplastic. So while polystyrene is a commodity thermoplastic, ABS is a quasi-commodity thermoplastic. And it is currently made, ABS, in 1.8 billion pounds per year. It has unique properties based on the combination of the 3 monomers that are used in the backbone. Acrylonitrile gives chemical resistance and strength. Butadiene enhances toughness and impact resistance and gives it low temperature properties, in other words, remains flexible at lower temperature. And styrene produces hardness, gloss, and enhanced processability in the formulation. Right now, various different companies do this. Right now, Bayer is the biggest one, but Dow still does quite a lot. GE Plastics as well. So you're looking at GE and Dow and Bayer as the big producers of ABS. Typically, ABS is produced by bulk polymerization, suspension polymerization, and emulsion polymerization. Typically, an ABS monomer composition is at least 50% styrene. They will vary the amounts of the butadiene and acrylonitrile. Sometimes they do this in a graft polymerization. Sometimes they will blend, which is a mixture of 2 polymers. So sometimes they will make styrene acrylonitrile and butadiene acrylonitrile, and blend those 2 together to give you an ABS. Typically, if a facility makes polystyrene, they also have the swing capacity to make ABS polymerization. ABS has low heat resistance. It is even less heat resistant than polystyrene. Again, it has the same problems as UV light. It yellows upon exposure to sunlight. It has a low tensile strength, and it is slightly hygroscopic. When you put in that acrylonitrile monomer, that starts to want to absorb moisture. So this does require drying before processing. Polystyrene and K-Resin have an advantage over ABS in this regard. ABS can be processed with all thermoplastic processing techniques: injection molding, extrusion, rotational molding, thermoforming, injection blow molding. The application areas for ABS include appliances, transportation, pipes, electrical and electronic components, medical applications, and of course, the miscellaneous category. Very frequently, ABS is used by original equipment manufacturers on appliances, like my washing machine. Appliance parts are a biggie for the applications of ABS. They have good impact resistance, so if you're going to run your vacuum into the wall, it's not going to shatter, but it has a nice finish. It's also used in automotive and transportation applications like instrument panels, decorative light trims, and steering wheels. Charloma uses a lot of ABS, and they use ABS with a foam core for buoyancy. Typically, ABS is used in pipes and fittings for drainage pipes, waste and vent pipes specifically. ABS, of course, is used in toys, garden products, furniture, trays, and then ABS is blended with other polymers as well. When we're talking about K-Resin, we're talking about 75% styrene and 25% butadiene co-monomer composition. And this is typically produced by Chevron Phillips, or Phillips 66. It was invented in 1967 and commercialized in the early 70s. And it has glass light clarity and durability. It's 90% light transmission. That means it's amorphous. And it's very favorable in packaging and marking economics because it's stiff yet flexible and has low moisture absorptivity. This has very high environmental stress cracking resistance, and it has very low permeability. It has very low moisture absorptivity as well and high impact strength. And so it has a yield advantage over the non-styrenic clear resins because it has low density, but it still remains clear. So this is compared to PMMA or PVC or polysulfone, which are much more dense. And so for the same truckload, it weighs less and therefore uses less energy. K-resin can be sterilized by most of the typical means of sterilization of reusable biomedical devices, and it qualifies as a biomedical material. It has been cleared by the FDA for packaging of non-fatty foods because it has a very good moisture barrier and extends the shelf life of food. This is also completely recyclable. It's considered a good commingler. There are two main types. There's KR01 and KR02. KR01 is injection molding applications, significantly higher impact than polystyrene, lower impact than KR03. This has advantages in that it has good warpage resistance, good stiffness, and good surface hardness. So there's the KR03 series. These are fairly chemically similar. And within K-resin, you can get gel content. And this is what is known as the fisheye defect. You get these gel particles, kind of look like a fisheye. And so here's the highest to lowest. Highest incidence of fisheye is in KR03 with the lowest of KR10. KR03 is used in injection moldings and in applications where these gel defects wouldn't be visible. KR04 is used in blend sheet extrusion. KR05 is used in blow molding, niche sheet extrusion, profile extrusion. And then K10 is used because it has the lowest gel content. This is for film extrusion, where you're going to see the whole film and you don't want those fisheye defects. The KR03 series contains a microcrystalline wax. This acts as an anti-blocking agent, and this improves the processing benefits. However, this wax can sometimes make it difficult to decorate. It repels inks, and so you can get certain grades without wax. And at this point, KR10 is not available without wax. So here are some selected properties in terms of density, yield strength, elongation, hardness, heat deflection, and light transmission. And light transmission you'll always see on something that has K-resin. So this is why you would use K-resin, is this 90% to 95% film extrusion, or sorry, light transmission property. This concludes the Styrenics. After this, we will move on to polyesters. And because we are done with the styrenics, we are also done with the commodity polymers. After this point, we will be talking about quasi-commodity thermoplastics.